Hello everyone, thank you very much for this opportunity to send our presentation as a video record and the fourth International Symposium on Infrastructure Development. This is Omar Al-Tuwaini. I am speaking on behalf of my colleagues. We discuss the submitted article about classification of air pollutants API intercorrelation using decision tree algorithms. Before I go on with my presentation, I would like to express our solidarity with the Indonesian people and all the people who suffered from the recent tsunami, and we just promise them that we will try our best to work on reducing the impact of such natural disasters. So I will pause this presentation for 1 minute, then I will continue. Thank you very much. Thank you. We'll go through the introduction, the objectives, and type study areas and the methodology. Then we will discuss the results and we conclude the research. Here I would like just to introduce my colleagues, Dr. Abdel Latif from University Petronas, and Dr. Ali Aida from Ibn Zuhr University, Morocco, and Dr. Trinas Gombo from Johannesburg University, South Africa. And this is Omar Al-Tuwaini from Ankara University. As you know that the air pollution represents the condition of air pollutant in the atmosphere at high enough concentrations within serious or above normal ambient level. The API with the air pollutant index is defined in terms of the effects of those pollutants on the human health. Therefore, the Department of Environment defines the API limits with a specific range from low to moderate to unhealthy, very unhealthy, and hazardous and risk. So the most daily index report comprise some of the major pollutant species like the O3B article matter 10 and the CO and SO2 and NO2. So in general in Malaysia, the air pollutant index value assessed with the particulate matter 10 indicator of the air quality, because commonly it's the highest value among those pollution species. The objective of the current study that we try to use a decision tree algorithm to find the intercorrelation between those dominant air pollution index and the other pollutants. As we mentioned, the API is taken from the PM10 and the other pollutants. So we want to know which of the factors that it's add or increase the value of the PM10 or contribute to this data using a decision tree. Data that we use, as we mentioned, it's based on the PM10 and the 4 other air pollutants, in addition to the 2 other meteorological parameters like temperature and the humidity. GIS also will be used to visualize and mapping the study area and with the surrounding environment. So here you see in the figure, the right side, it's the values for each pollutant the range for the current study. A study area, Penang Island, Malaysia. So the major sources of the air pollution are the mobile sources, which contribute almost 70%, stationary sources, and the open burning sources. And those SO2 and O2 and the O3 in the study area caused mainly due to the compensation process from the vehicles and the industries. So the city is growing, also the population is growing very fast, and it's concentrated in the urban industrial areas, which is as a result increase the volume of vehicles. Wind movement from Sumatra Islands carry open burning particulate matter, which increase the API as well. To 22 months record of this active monitoring station in Penang were collected. The methodology, we started with the data collection. So data was collected from just single air monitoring station located in the USM for 22 months, March 2005, the end of 2006, and it's hourly data. Then in the additional of the temperature and the humidity, as we mentioned. Also, there is 4 decision trees were tested and compared. So it's the posted C5 and the random forest, PIRT, and then nave-based tree. 4 decision trees. Adding to this the classification and regression tree card package that used many algorithms to plot simplified the bounded tree and split attributes based on the sum of the square error. So the API was used for in place of the real values for the pollutants, except the humidity and the temperature. We'll use the real values. About missing data, there is no missing data in this study. That's why we didn't use the imputation technique here. So that the value of the API, especially for the PM10, because we took it as the dependent factor, while the other species are the independent factors. So that's we will test PM10 with the relation to the others as dependent and independent relationship. So that's why we converted the API of the PM10 into 10 percentiles. Then we can see, we can give more freedom to the species to show the correlation with the high value of API or the low value of API. So the first step is decision tree classification. Is the learning process. So we divided the data into training and testing. The training data, it's from March to 2005 to October 2006. The testing data we left from October to the end of 2006. So this study, the temporal scale of data, it's limited. It's just to 22 months. So we just left 2 months for testing, because if we reduce the data in the training stage, the model won't behave correctly. If we have more data span, we can also investigate more training data, because especially in data mining, it is the most important part. It's the training data. As a result, you see here on the right side, it's the decision tree that classify the relationship with the most effective factors between PM10 and the others. So if you see here the P20, P30, this is the percentile of the API. So you can see here CO, it's working fine for the first classification order. That means the CO, it's the most common and most correlated, which is also mentioned here in the figure on the upper left side, that the CO, it's contribute the highest. Okay, this is a Gini plot for the random forest tree, showing that CO and the O3 are the most significant factors connected to the API, while the NO2 and the air temperature are the lowest contributors. Also here in the table 3, you can see the values of the prediction using this algorithm, the variable importance based on those 4 algorithms. We see that the C5, it shows us the highest classification, while the prediction as well, it's, as we mentioned, because it is just 2 months, so it's still tricky. If we increase the training data, we can get better prediction rate. As well, as you can see, is naive Bayes tree, it shows the lowest value for the classification and the prediction, while the rest of the root mean square error and kappa index within the acceptable range. So as we discussed here, the kappa index of the observed level of agreement fall within 0.6 to 0.8, which is a good agreement. That's why the PIRT algorithm with this range agreement was obtained, because here in the BC5 we couldn't get the clear value of the kappa index, so we refer to the one that it shows us the clear value as well as the classification. And so far, as we mentioned, the prediction here within 50%. It's kind of just 2 months. Using this as a pilot study with the long term of data, they will be presented in the complete article will be published later. So all the algorithm agreed that CO is the most correlated pollutant with the PM10 on the both resources are produced by incomplete composition, that is mentioned in the table 1, while second pollutant CO and O3. All the algorithm agreed on the limited role of humidity and the temperature with the PM10. This likely due to the characteristics original composition of the particle matter that are produced mainly by the anthropogenic factors. However, considering the wind direction and wind speed may add more contribution value. And auto variables show the low intercalation with importance with the PM10. This can be ascribed to its original chemical structure that is generated by oxidation of NO to NO2 in the atmosphere. So it's mainly produced by power plants, while vehicles and industries are major source of SO2 and PM10 and SO. In figure 4, we saw that the R-part algorithm produced short tree using 8,200 nodes. This every node it represents 1 day, and it is just out of 14,000, which represent the training data. That means it just took about 70 to 60% of the entire training data successfully classified, as we show in the classification table for the R part. 80% of this 8,200 node fall between the percent 20 to 40. That's equivalent to the value of 33 API, while value of a CO API recording during the entire period range between 4 to 7, with mean value of almost 6, which is classified as healthy on the API scale. Nevertheless, this study aimed mainly to find the intercorrelation between the PM10 and the other pollutant, rather than detect the high or low concentration of the API. CO API value, which represent the most important variable among the others with the correlation with the PM10, is smaller than 6.5. That means it can refer to P20 of PM10. Looking at the P20 with 70% of the nodes with more focus, this can represent by the O3. If O3 is less than 38, it can refer to P20, else it refers to P30, which is this one what we are talking about. In the figure 4b, which is a conditional interference tree of the PM10 with the other pollutants as well, this one by using the tree algorithm. So we notice that tree algorithm shows similar classification with the R-part algorithm, which is the figure 4a. except the leave of the SO2 that added the range of value less than 5.5 API to be contributed in addition to the O3 less than 37 API, which is excluded the P30 to match the SO2 value more than 5.5, and that is why SO2 has controversial role of importance higher or lower than O3. So to sum up, in the current study, we described several types of decision trees algorithms to find the intercorrelation between dominant air pollution index for PM10 percentile values and the others air pollutants like SO2, O3, NO2 and CO, as well as the temperature and humidity in Penang Island, northern Malaysia, with the data of 22 months. The study found that SO and SO2, CO, SO2 and O3 are the major pollutants significantly intercorrelated with the PM10 and contributing to degradation of the air quality in the Penang Island, and that occur mainly due to the combustion process from the transportation modes like hybrid vehicles and developing industries. PIRT and random forest show the most stable algorithm by introducing clear decision about the most important variables that intercorrelate with the API value of the PM10. Also, our programming show very nice and stable analysis rhythm in terms of producing those decision trees, and that's to conclude that more data need to be used to understand why NO2 show mild importance result, as well as using the wind direction and speed. Wind speed will definitely contribute as added value to the current finding. Eventually, using decision tree as environmental metric analysis technique help to better understand the air quality pattern of the main pollutants that contribute to the high API value in the study area. So before we end, we would like to acknowledge that the author gratefully acknowledge the financial support from the University Technology Petronas Strive Research Project grant. Also, very grateful to the Department of Environment Malaysia for providing the air quality data used in this study. Thank you very much. شكرا لكم على الإصغاء. Please, if there are any questions or there is any inquiries about the data process, code and the relevant data, don't hesitate to email me on the altawani@ankara.edu.tr. So thank you very much again, and I wish you a very good day. This is Omar Altawani from Ankara University.